Okay, here we have a rational function s squared plus 30s plus 1 over s cubed plus s squared minus 8s minus 12. And the question is to determine the inverse Laplace transform of this function. The form of the function suggests using partial fractions. To use partial fractions, the first step is to factor the bottom. So let's take a look at the denominator, s cubed plus s squared minus 8s minus 12. And let's see what in the world the possible rational roots of this could be. So the possible rational roots are equal to, okay, so the numerator must be things that go into the constant term. So the factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then the denominator must be things that go into the leading coefficient, which is 1, so just plus or minus 1. So dividing, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Those are our 12 possible rational roots. Now, there's obviously not all 12 of them will work. It's a cubic polynomial, so only at most 3 of them could work. Also, there's no guarantee that any of these will actually work. In fact, the only guarantee that you have that any one of these will work is the benevolence of your instructor. There's no a priori guarantee that any of these will work, except for the fact that this problem was carefully chosen so that one of them would work. Okay, now how do we find it? Well, we just start testing. So here we go. 1, 1, negative 8, negative 12, and let's use synthetic division to see if 1 works. Okay, so 1 times 1 is 1, 1 plus 1 is 2, 2 times 1 is 2, negative 8 plus 2 is negative 6, negative 6 plus 1 is negative 6, negative 18. Doesn't work. All right, 1 down, 11 to go. Let's try 2. 1, negative 8, negative 12. Implying synthetic division, we get 1 times 2 is 2, 1 plus 2 is 3, 3 times 2 is 6. Negative 8 plus 6 is negative 2. Negative 2 times 2 is negative 4. Adding negative 16. Doesn't work again. Okay, let's try 3. We get 1, negative 8, negative 12. So 1 times 3 is 3. 1 plus 3 is 4. 4 times 3 is 12. 12 minus 8 is 4. 4 times 3 is 12. And finally, we get one that works. So we've established that this polynomial is equal to, we found that 3 is a root, so s minus 3. And we've also found the quotient. So this is going to be constant linear quadratic, s squared plus 4s plus 4. And if you directly multiply this out, you should get exactly this. Now, from this point forward, hypothetically, we can continue testing rational roots. Let me just make a comment about this. So now the constant term is now 4, and so that eliminates 6 and 12 as possible rational roots, because the constant term is now 4, so we can't have 6 and 12 be rational roots. Also, we have a constant term of 4 here, so 3 is not going to work a second time. So we're down to 6 possible candidates, 1, 2, 4, plus and minus. And actually, we've already tested 1 and 2. So if we were to keep using synthetic division, there's only 4 numbers to test, 4, negative 1, negative 2, and negative 4, because of the work. So the idea is that synthetic division gets easier as you go along because the list of candidates gets shorter. Now, in this case, we could use synthetic division, but it's a whole lot easier to simply factor what's left. It's quadratic. And so this factors as s minus 3 and s plus 2 quantity squared. And so there is the complete factorization. We see that negative 2 is actually a double root of this denominator. Okay, so continuing the problem, find the inverse Laplace transform of s squared plus 30s plus 1 over this. So this is s squared plus 30s plus 1 over s minus 3 times s plus 2 squared. And so now we have to find the partial fraction expansion. So we have a over s minus 3. We have one term that corresponds to this. We also have two terms, b over s plus 2 and c over s plus 2 squared, that correspond to the s plus 2 squared term. The bottom is cubic, so not surprisingly, we have three unknowns, a, b, and c, that we have to solve for. Clearing out the denominator, we get s squared plus 30s plus 1 is equal to a times s plus 2 squared plus b times s plus 2 times s minus 3 plus c times s minus 3. And so that is the equation that we will use to find what a, b, and c are. Okay, from this point forward, there are two possible options. Method number one, which I would not particularly recommend for this problem. Method number one is let's multiply out the right-hand side. S squared plus 30s plus 1 equals, multiplying out, we get a times s squared plus 4s plus 4 plus b times s squared, then I've got minus 3 plus 2 makes minus s minus 6, plus c times s minus 3. Okay, then over here I have 1s squared has to be equal to a s squared plus b. Then the 30s has to be equal to 4a. Then we have minus b plus c. And then lastly, the constants, 1 has to be equal to 4a minus 6b minus 3c. And we get a system, a 3x3 system of equations that has to be solved for a, b, and c. Again, this works. 3x3 systems can be solved, but it's a little bit more work than I really want to do. So this technique works, but I wouldn't recommend it for this problem. Instead, let's take a look at a second method. Method number two. Method number two, let's plug in some numbers that are convenient. Let's plug in negative 2. I choose negative 2 because if s is equal to negative 2, this is 0, that's 0, and the only thing left is going to be a negative 5c on the right-hand side. If I plug in negative 2 over here, I get 4 minus 60 plus 1. So negative 55 is equal to negative 5c, so that c is equal to 11. Okay, now the other thing that I could plug in that is going to be pretty simple is going to be plugging in s is equal to 3. If s is equal to 3, then this goes away and that goes away. The only thing that's going to be left is 25 times a. If s equals 3, I get 9 plus 90 plus 1. And so that gives me that 25a is 100, so that a is equal to 4. Okay, so that's two things. Now, to get b by itself is not going to happen, right? Because if I plug in 3 to make this go away, then this goes away also. If I plug in negative 2 to make this go away, then this also goes away. So getting b by itself takes a little bit more thought, and the thing that usually works here is let's just plug in anything else that's convenient. So let's plug in s equals 0. Just plug in anything else. The left-hand side becomes 1. Let's work with this. If s equals 0, the left-hand side becomes 1. The right-hand side becomes 4 times a plus 2 times negative 3 times b plus negative 3 times c. Now we just got done figuring out what a and c were. A was equal to 4. Here I get minus 6b. Also earlier we figured out that c was equal to 11. And so we can isolate b all by itself. So 1 is equal to 16 minus 6 times b minus 33. So 1 is equal to negative 17 minus 6b. So that makes 18. equal to negative 6b, so that b is equal to negative 3. Okay, so the practical effect is that this becomes a was equal to 4 over s minus 3. B is negative 3 over s plus 2. And then c was 11 over s plus 2 squared. And so that is the partial fraction expansion of this left-hand side. Okay, now the last step is the differential equations part of the problem, which is to find the inverse Laplace transform. Up until now, this has been basically techniques from pre-calculus or maybe calculus 2. But now that we have the partial fraction expansion, we can find the inverse Laplace transform. Now to do this, let's take a look at our table of Laplace transforms. Okay, first off, we see that this part here matches this formula. So I get, instead of s minus a, I have s minus 3. So I should have e to the 3t over here. So 4 times e to the 3t. Here I have s plus 2. So instead of s minus a, I should have s minus negative 2. So minus 3 e to the minus 2t. Okay, now this last one doesn't fit this pattern because I've got a square. So I have to go a little bit further down the table for this one. And if I go further down the table, I see that I've got this pattern here. S minus a to the n plus 1. And that is supposed to fit. Let me see if I can get both of these on the screen at the same time. I'm going to be using this formula here because my inverse Laplace transform look like this. So I have s minus a to the 2 squared. So my 2 here is 1 plus 1. So just taking a look at this part all by itself, that's 11 times 1 over s squared to the 1 plus 1. So I have a 1 factorial, there's the 1, then I have n plus 1, and so this pattern is what I'm going to use. So my n is 1, so t to the first, my a is negative 2, and so therefore I conclude that the inverse Laplace transform of this part is going to be plus 11 t e to the minus 2t. And that is going to be the inverse Laplace transform of this function.